An ellipse has 5 degrees of freedom. So if you want to specify a particular ellipse, you need to pin down 5 points. A circle is a special ellipse, so we would expect that we require more restrictions to make sure it actually is a circle. More points, for example, or maybe points in a special arrangement. But we all know that a circle is uniquely determined by 3 arbitrary points on it. Somehow we lost 2 points. I'm Bernhard Werner, and this is a video about how the right coordinate system can help resolve geometric edge cases. To properly describe ellipses, circles and the differences, we need a suitable coordinate system. One which can deal with perspective distortions. After all, if you draw a circle on a piece of paper and look at it from an angle, it will look like an ellipse. So we have to deal with that. If we also have a grid on our paper, and when we extend the grid lines, we see that parallel lines intersect. We call these points the points at infinity. In art class, you might have called them vanishing points. Finding a model which deals with them will unlock most of the tools we need to understand the rest. Looking at the grid straight now, we can describe a point at infinity by specifying a certain direction. All lines that run in that direction will meet there in perspective. We can add coordinate axes and specify such a direction towards infinity with an x and a y coordinate. But we also use x and y coordinates to describe the positions of ordinary finite points. That means coordinates come in 2 flavors. They describe either finite points directly or infinite points as the direction those points can be found at. For simple bookkeeping, we could just write those 2 versions of coordinates differently. However, we want a unifying coordinate system in which we can work with both types of points the same way. Only if we want to explicitly know whether a point is finite or infinite, we want to be able to check. To find such a coordinate system, we look at the main difference between positions and directions. The latter aren't unique. If we consider the direction given by the coordinates x and y, and the point at infinity it represents, then any non-zero multiple represents the same direction. So we want to be able to multiply our coordinates by any number not equal to 0 and get the same object. Note that we do not care about the orientation. Lines that run in that direction shall only meet once at infinity. So a negative multiple represents the same point at infinity. Of course, for finite positions, this doesn't make sense right away. Feel free to pause at this point and ponder how you would do this. We want to be able to arbitrarily scale our coordinates because it is necessary for directions. But for ordinary positions, we need to be able to reconstruct them somehow from any of the multiples. The solution looks like this. We add a third coordinate, a 1 if the coordinates represent a finite point, and a 0 if it represents a direction pointing towards an infinite point. Additionally, we say that any of these now 3D vectors represents the same 2D point if they are a non-zero scalar multiple of each other. For any vector, we denote the set of all these multiples with these square brackets. But often we won't write the square brackets, we just remember they exist. Let me repeat it for emphasis. While this bracket set contains infinitely many 3D vectors, it represents as a whole a single 2D point. We call any such 3D vector that represents a 2D point the homogeneous coordinates of that point. For vectors with set not equal to 0, we can always divide by the set coordinate to force a 1 there and get the original positions in the x and y coordinates back. And for vectors with a set coordinate of 0, this immediately works as we wanted. Their x and y components represent a direction, and any multiple will give the same direction. This way, there's never confusion which point any such homogeneous coordinate vector represents. Note that we have to exclude the 0 vector as a potential representative. With a 0 in the last coordinate, it would have to be a direction, but the 2D vector 0, 0 doesn't point anywhere. Apart from that, all vectors in R3 are valid representatives of either a finite or infinite point. If you find all of this a bit sketchy, know that it is very similar to how fractions work. A fraction as a whole can be scaled by any non-zero multiple without changing its value. And integers can be made into fractions by adding an extra 1 at the bottom, so to speak. Only fractions with a 0 in the denominator don't make sense, but you might be familiar with the idea that dividing by 0 gives infinity. So it's not the same, but you can think of homogeneous coordinates a little bit as some sort of fraction where the numerator is a 2D point. To see that we can actually do proper geometry in a useful way in this coordinate system, Let's look at how lines work and make our way up to circles from there. A line in the plane can be described by a linear equation like this. The coefficients a and b form the normal vector of the line, and the constant term c describes the distance of the line to the origin. Let's look at a concrete example. 2x minus 3y minus 4 equals 0. An ordinary 2D point lies on it if its coordinates fulfill this equation. Here, for example, the point 5, 2 does. If we now go over to homogeneous coordinates, we run into two problems. First, this point can be represented by the vector 5, 2, 1, and those coordinates still fulfill the equation. But the point is also represented by any multiple, for example minus 10, minus 4, minus 2, and these coordinates don't fulfill the linear equation anymore. Secondly, since the line goes off towards infinity in the direction 3, 2, the point at infinity there should fulfill the equation too. It is represented by 3, 2, 0, and those coordinates don't work in the equation either. We can fix both by using the additional set coordinate we have and add it in the only place that looks right, multiplied to the constant term. This is now a so-called homogeneous or homogenized equation. Now both 5, 2, 1 and minus 10, minus 4 and minus 2 fulfill the equation. Moreover, the expected point at infinity, 3, 2, 0 in the example, now also fulfills it. It is often convenient to gather the coefficients in their own vector and write the equation using the scalar product of this line vector and the indeterminate point vector, which is literally just the expanded equation at the top. Another thing that should work here in this system is the two parallel lines intersect at a point at infinity. After all, that was the reason we introduced them to begin with. Let's see how that works. With homogeneous coordinates, we can directly write down intersections. Given coefficient vectors of two lines, parallel or not, their intersection point P must fulfill LP equals 0 and MP equals 0. This is fulfilled by the cross product of the vectors L and M. We have an explicit formula for it and can use it to check that it works. More conceptually, the cross product is often characterized by being a vector that is perpendicular to two given vectors in 3D. Being perpendicular can be expressed by the scalar product of the involved vectors being 0. And that's exactly what we have here. Note that it is crucial now that we use homogeneous coordinates. The line in the example has coefficient vector 2, minus 3, minus 4. We can compute its intersection with the line minus 2, minus 6, 4, and the resulting cross product is minus 36, 0, minus 18. As described earlier, we have to divide by the set coordinate to recover the correct intersection point at 2, 0. Let's look at two parallel lines next. Their normal vectors point in the same direction. Without loss of generality, we assume that they are equal. That means the coefficient vectors of the lines will have the same first two entries, something like this. Then their cross product will have a 0 in the last coordinate, which means it is a point at infinity, as it should be. Moreover, we can factor out d minus c and see that the direction this point lies in is given by b minus a, which is precisely the direction in which the lines run. Lastly, note that all points at infinity fulfill, by definition, the linear equation z equals 0. So they all lie on a line with coefficient vector 0, 0, 1. In the non-homogeneous version of the line, it would be the equation 1 equals 0, which is always wrong. So no finite point lies on it. We call it the line at infinity, and it's just the line you see in a perspective drawing on which all vanishing points lie. We will denote it by L index infinity. So it appears that these homogeneous coordinates we defined can deal with infinity in the right way. Let's see how that helps us with circles and ellipses. Both circles and ellipses are described by quadratic equations, but so can parabolas and hyperbolas too. We will have to look at all of them to thoroughly understand what's going on. Since these are described by quadratic equations, they are called quadratic curves. But they also arise as intersections of a cone and a plane in 3D and are therefore also known as conic sections, or conics for short. A quadratic equation in 2D in general looks like this. We now have exactly the same problem as before. When we want to check whether a point lies on such a curve, we have to check whether the equation is fulfilled by the coordinates of the point. But if you use homogeneous coordinates, we need to be able to use any scalar multiple of them. In the same spirit as with lines, we homogenize the equation by filling up every summand with extra sets until their degree is the same, in this case 2. To see that this works properly, let's do a small example. The unit circle can be described by the equation x² plus y² minus 1 equals 0. After homogenization, the -1 turns into a minus z squared. The point 4/5, 3/5 lies on the unit circle, and its standard homogeneous coordinates are 4/5, 3/5, 1. But it is also represented by 4, 3, 5. Using those coordinates in the homogenized circle equation, we get, indeed, that 4 squared plus 3 squared minus 5 squared is 0. Next question. What are the points at infinity of conics? For ellipses and circles, it is not obvious how that should even work, but parabolas and hyperbolas clearly run off towards infinity in some sense. So let's start with them. The standard hyperbola is given by the equation y equals 1 over x, or in our system, as x times y minus 1 equals 0. Homogenized, the left-hand side is xy minus z squared. If a point at infinity lies on it, it has z equal to 0. Its other coordinates, x and y, then must fulfill x times y equals 0. This happens if either x or y are 0. Recall that it's not allowed for all coordinates to be 0 at once. That means if x is 0, the homogeneous coordinates must be 0, 1, 0, or a multiple of that. And if y is 0, we get 1, 0, 0. These are the points at infinity of the y and x axis respectively. When we look at the image of our hyperbola, we see that it gets closer and closer to the coordinate axis and seems to follow their direction. Just from a visual inspection, it makes sense that we got the points at infinity we got. What about parabolas? Let's take a simple one, like y equals x squared. Rearranged and homogenized, we have x squared minus y times z equals 0. Again, if a point at infinity can be found on this curve, it must have z equal to 0, which leaves x squared equals 0 for us to solve. We get 0, 1, 0, or any of its multiples as the solution, which is the point at infinity of the y-axis again. Note that this is a double solution of the equation x squared equals 0. That means the parabola intersects the line at infinity twice in the same point. Looking at the parabola, it might be a bit harder to convince yourself, but both sides of the function graph do in fact become more and more vertical and therefore hit the point at infinity, which is straight up. We now want to do that for ellipses too. If we take this one for example, homogenize it and set z to 0, we see that the resulting equation cannot ever have a solution, unless all coordinates are 0, since squares of non-zero coordinates are always positive, and the 0 vector is still not allowed. And while we will soon see that there's more to it, let's recap for a second. We only looked at examples so far, but it's straightforward and a bit tedious to check that no ellipse intersects the line at infinity. All parabolas will intersect it once in the direction of their symmetry axis, and hyperbolas will intersect it twice at the direction their asymptotes run towards. And this is about the easiest way to check whether an arbitrary conic section is a hyperbola, parabola, or ellipse. You compute the number of intersections with the line at infinity. In particular, if you look at a perspective drawing, any conic can look like any else. The only way to recognize them is to keep track of where the line at infinity lands and check these intersections. Now, if you have a bit of experience with solving polynomial equations, you might know that even if you can't find real numbers that solve them, you can always find complex numbers that do. So let's quickly go through what we need to know about them before we see what they can reveal about geometry. The complex numbers are a way to extend the real numbers we are used to. This is done by adding a special number, usually called I, which fulfills that I squared is minus 1. Of course, no real number has this property, so this is definitely beyond our ordinary number system. Then any other complex number can be written by taking two real numbers a and b and write a plus b times I. If you have two such complex numbers, you can add and multiply them using the associate, commutative and distributive properties as you are used to. Take 2 plus 3i and 4 minus I for example. We can add them by simply adding the summands without I and the summands with I in them. If we wanted to multiply them, we expand the expression to get 4 summands. The last one contains I squared, so that simplifies to just minus 1. Then we add all summands we can add. Now, in my opinion, it is not the best way to think about complex numbers as this extension of the reals by the square root of minus 1. But for our purposes here, this is precisely what we need. Numbers of the form a plus bi, with which we can make ordinary calculations, always remembering that I squared is minus 1. Why and how to even come up with such a construct is a topic for its own video. Back to ellipses and back to the example from before. We already set z to 0 since we are looking for points at infinity. Since x and y are not allowed to be 0 at the same time, without loss of generality, assume that y is 1. This leaves a relatively simple equation in x. When we try to solve it, we get that x has to be plus or minus square root of minus 2. Normally, this would be impossible. But with complex numbers, we can write this as square root of 2 times I. So this ellipse has points on it that lie on the line at infinity, but they are quote-unquote invisible since they have complex coordinates. If you do this calculation for circles, you will notice something peculiar. Those complex points at infinity will always be the same, regardless of which circle you start with. Concretely, it's these two. Let's quickly check that this works. A circle with radius r around the point mx and my can be described by this equation here. Expanded, sorted and homogenized, we get this. Setting z to 0 gets rid of the complicated terms, then setting x to 1 and y to I quickly yields a 0. So the point I fulfills this equation and the calculation for point j is basically identical. A more geometric intuition for why these points at infinity are always the same. If one conic is a translated and scaled version of another one, their points at infinity are the same, because translating and scaling directions doesn't change where those directions point to, and all circles are just translated and scaled versions of one another. So all their points at infinity must be the same, even if they have complex coordinates. Note that our usual idea of Euclidean geometry completely breaks for these 2 points. Since they sit on the line at infinity, they should be infinitely far away from any finite point. But since they also lie on every single circle, regardless of radius and center, they should at the same time be every possible finite distance away from every point. The notion of distance really doesn't make any sense whatsoever anymore for these points. Getting back to our previous classification, we can make it a bit more precise and add circles. Hyperbolas intersect the line at infinity in 2 real points. Parabolas intersected at a real double point. Ellipses intersected in 2 complex points, and circles intersected in 2 specific complex points, namely I and j. This resolves the conundrum from the start of the video. To specify an ellipse, or any conic for that matter, we need 5 points in general. The reason is that the quadratic equation of a conic has 6 parameters, a through f. Since not all of them can be 0, we can always assume that one of them is equal to 1, which leaves 5 that need to be determined by specifying points on the conic. And since all circles have 2 points on them already predetermined, namely I and j, we can do with less here and only require 3 custom points for any circle. Now you might think to yourself, fine. Technically, all circles intersect in these points I and j, but they aren't real points. Quite literally, since they have complex coordinates. And after all, I myself said that our ordinary understanding of Euclidean geometry doesn't work for them. And while this is certainly true in a sense, if we do pretend that they are ordinary points, like all the others, we can use them to do some neat constructions. To end this video, I want to show you one, but without any explanations. Just to show you the vibe. Let us assume that we have a perspective drawing of the plane, i.e. the line at infinity isn't at infinity anymore, but finite and visible. For a given line G and a point P, we might ask how to find the perpendicular to G through P. For that, we need I and j. Assume that we could actually see them on the line at infinity, like this. Then we can do the following construction. We connect I with P, intersect a new line with G, and connect the intersection point with J. Similarly, we connect J and P, intersect with G, and connect to I. Finally, we intersect the resulting 2 lines and connect that point with P. This line is then the perpendicular we wanted. Of course, it doesn't look like it's perpendicular to G. Firstly, I and j are depicted with real coordinates here, and secondly, it is a perspective drawing after all. We can fix both by moving I and j to their actual coordinates and drag the line at infinity after them. Note that all auxiliary lines and points vanish as their coordinates become complex too. But in the end, the resulting line is real again, and it actually looks as perpendicular as it is supposed to be. Moreover, the last intersection point we constructed turns out to be the mirror image of P with respect to G, which is nice. That means, as long as we keep track of where I and j land in a perspective drawing, we can still construct/compute perpendiculars with them. So, while I and j themselves cannot be properly interpreted in Euclidean geometry, they can be used to do Euclidean constructions. Apart from perpendiculars, these points I and j can be used to find many other things. For example, the focal points of conics. They also serve as the connection to entirely different types of geometries, like hyperbolic geometry or relativistic spacetime geometry. But this is a topic for another video. With that, thank you for watching and until next time.